couple months ago, where we're trying to bring together some of our academic partners that are part of DC-MUSE with some of the industrial researchers that have been part of our community and that are interested in the work that we're doing. So today, we have a very exciting set of talks focused on electrified reactor technologies. And before we get started, let me just tell you a little bit about DC-MUSE in case you're new. DC-MUSE is a network that involves multiple academic researchers across more than 11 universities, which is really focused on helping us to find ways to decarbonize chemical manufacturing via electrification. I think many of us know that there's multiple pathways to achieve these, either by leveraging electricity and retrofitting our current technologies that are based on thermal processes to be able to bring electricity as a power source and perhaps decarbonize energy utilization within our plants. But at the same time, our team is also focusing on longer-term technologies, which are based on electrochemical reactors as well as plasma reactors, which you will see as part of this series in future events. But today, we're really going to be focusing on electrified reactor technologies for low-carbon chemical manufacturing in general. And the first speaker for today is Professor Mike Harrell from University of Houston. I think probably many of you know Mike because Mike is really an authority in reaction engineering in this field. So we're very lucky to have him present today. So he's currently the Cullen Engineering Professor of Chemical and Biomolecular Engineering at University of Houston. So Mike started his career in academia at University of Massachusetts in 1985 before moving to industry, where he worked at DuPont for about 7 years, and then came back to academia to University of Houston, where he served as department chair for 16 years. So Mike have been very active.
हाँ नहीं नहीं बच्चों के साथ सुबह फोन आया
You possibly mute your mic.
ये दीदी के बच्चे कहाँ जा रहे हैं?
Could you help me, Simon, mute? Thank you. Apologies about that. So that's saying Mike is really an authority in reaction engineering. It's very, very visible.
I think Miguel got muted.
All right, so let's try this again. So as I was saying, Mike have been very active in our chemical engineering community, have served as editor-in-chief of the AICHI journal, have served as chair of the CRE division in AICHI, and as president of ISCRI. So without further ado, I'm going to stop sharing my screen, and I'll invite Mike to share his and tell us a little bit about the work on electrified reactors. So thanks everybody for being here.
Okay. Thank you, Miguel. Let me get the slideshow going here. Hopefully everybody can see that. Okay. Miguel, are you able to see that, Simon?
No, we can't see your slide, Mike.
Just a second here.
All right, we got it.
Good?
Yes.
Okay. And everybody can hear me, hopefully.
Yes.
All right. Good morning, everybody. Thank you, Miguel, for the nice introduction, and it's great to join everybody this morning. I think it's a great time to be a chemical engineer, especially in the area of catalysis and reaction engineering. We face a lot of challenges on sustainability, and hopefully today you'll see some of those challenges come through in my short talk together with Ram Ratnakar. Now, this is research that I'm carrying out together with my colleagues Vamiri Balakataya and Praveen Bellini, and the work till now has been supported by Shell. Now, in a paper that Darek Malapragada co-authored, we painted a picture of the different types of electrification that are possible with reactor technology. And these are 4 such modes: direct heating, electrolysis, various electrochemical reactions, and finally plasma. Now, today I'm going to touch upon briefly some of the work that we've been doing as part of DC-MUSE in the area of plasma, and then move to direct heating, ohmic heating for catalysis. So this first vignette that I'll touch upon is looking at the use of plasma with catalysis in converting alkanes to olefins and hydrogen. Now, this is work that I've been doing with my colleagues Vince Donnelly, Lars Grabau, and Ryan Hartman at NYU, supported by a grant from NYU and the Sloan Foundation. Now, as part of that, project, we've defined a potential use of plasma that would really change the game in terms of olefin production. Now, I'm going to show you a small piece of that concept. Here we have a flow diagram that connects a plasma conversion step with a hydrogenation step. The idea is to utilize natural gas alkanes together with plasma and possibly a hydrogen permeable membrane to co-produce hydrogen on one side and alkynes and olefins on the other. Basically, the plasma would serve the purpose of breaking the hard bond to break the CH bond of methane and gradually build up molecular weight into lower molecular weight unsaturated hydrocarbons. Now, just to show you the potential of this approach, I'll show you some data where instead of methane, we fed in ethane into a small plasma reactor in our lab here at University of Houston. Now, as you might expect, the plasma creates a mess in terms of the chemistry. And this is basically the raw data out of a mass spectrometer downstream of this small plasma reactor when the ionization energy is at 70 electron volts. You can see that there's a very complex mass spectrum that includes lower molecular weight olefins and hydrogen, for example. Now, with the expertise of Vince Donnelly, we can tune the ionization energy to remove the fragments produced by the mass spec. So when we do that, it's interesting what emerges is a very clean spectrum now where we can be sure that the products we're looking at are a result of the plasma upstream, not the mass spec ionizer downstream. And you can see, interestingly, there's a family of olefins C2 to C7 that are obtained from this non-catalytic plasma application of ethane. Now we're continuing that study, and I just wanted to show you what's possible. Now, one might argue that's not very practical because we're producing a very complex mixture of olefins and so on, but the purpose of this project was to see what's possible, and then we do the engineering from there. Now, I'm going to go back. So ethane to higher olefins and hydrogen. Now, let's go back to the different modes of electrification. I'll spend the rest of my time talking about methane e-reforming or methane steam reforming using ohmic heating. And again, this is with my colleagues, Bala and Praveen. Now, as we all know, steam methane reforming is the major route to hydrogen in industry. 90 to 95% of the hydrogen is produced that way in these large complexes all around the world. There are two main reactions in methane steam reforming. It's a catalytic reaction. Typically, nickel on alumina is the catalyst. Methane steam reforming, together with the reversible water gas shift reaction, gives a product that is basically syngas with some CO2 as well. And then one in the process proceeds to purify the hydrogen as one product from this process. Now, the conventional steam methane reforming is produced in these huge reactors that are supplied with heat through combustion of fuel. SMR, being a strongly endothermic reaction, requires a lot of energy to not only heat the feed up to reaction temperature, 700-800 degrees centigrade, but also to eclipse the heat of reaction in the endothermic chemistry. Now, these are reforming tubes filled with catalysts that are in contact with the very hot furnace, and the chemistry proceeds quite nicely. Now, unfortunately, this process really up until recently, one didn't really worry about methane steam reforming, but with the advent of sustainability issues around greenhouse gas emissions, we have a new problem on our hands. Now, hydrogen continues to be a very strongly growing industrial chemical and predicted to accelerate in demand over the coming years as we approach the middle of the century. And again, as I mentioned, the way hydrogen is made is in these burners that unfortunately produce a lot of CO2. And in fact, SMR is a CO2 hog. On the order of 10 kg of CO2 per kilogram of hydrogen is produced in the process. So with the need to reduce greenhouse gases, this is a natural reaction system to look at as an electrification application. The idea being that instead of burning fuel to generate CO2, one uses electrons from renewable sources, be it solar or wind, and so on. So let me just mention, this is an active area of research and industry. These are a couple recent efforts around the world. SABIC, BAS, and Linde are collaborating on an e-steam cracker in Europe. Dow and Shell are also exploring technology on electrified steam cracking. Now, ethane to ethylene, of course, is also an endothermic reaction. So a lot of interest in industry and a lot of interesting fundamental questions that we can undertake. Now, my colleague Vamiri Balakataya and his former student Ram Ratnakar, who you'll hear from later this morning, wrote a very nice paper during my last year as editor of the AICI Journal, where they laid out different kinds of electrified reactor configurations that would hold promise for carrying out endothermic reactions. Their focus in this particular paper was ethane to ethylene. And as you can see, these are very unusual reactors that involve wires, strips, monoliths, and meshes that are electrically conductive, but can be heated by passing a current through a material like fecroloi or nichrome, as we all know in our homes. Now, in this study, Ram and Bala went on to show that one can start with a basic unit that can be scaled out in terms of modules, building an arrangement of modules, which with individual control over the applied voltage of these basic units. The idea being that the multi-modular unit would then be placed in a distributed manufacturing kind of application where the power would be also distributed and applied from, say, wind turbines out in oil fields in West Texas, for example. Now, after this paper, Bala walked down the hall and asked me, do you want to collaborate? And of course, I said, absolutely. Bala is a great guy to collaborate with. And he said, we have some interest in Shell to pursue some reaction engineering aspects of this problem. So I thought this looks interesting. It shouldn't be that hard. After all, if I go home to my kitchen, I have plenty of operational experience plugging in a toaster and toasting some bread. And there you see the hot wires that are electrically heated. Why not just flow in steam and methane and slap on a GC and we're done? Well, It's not that easy. As research goes, there are surprises, and I'll try to hit upon those in my remaining time. So we went to the lab, prepared a single wire coated catalyst with the wire being fecraloy, F-E-C-R-A-L, alloy, that is a well-known material for Joule heating. We would coat that wire with a SMR catalyst and then put that into a reactor. Now, the details of this work are shown in this reference right here on the slide. Now, here's a picture of a coil that we work with. So this is a 0.5 millimeter OD fecraloy coil, about 45 centimeters long, wrapped in 11 turns of about 1 centimeter diameter. We apply a voltage across the coil. Before we do that, we coat that coil with a nickel zirconia catalyst. That's fairly standard stuff. We have a lot of experience coating monoliths and foams and so on. This is no different than that. What we end up with, if successful, is a good adhering zirconium oxide film impregnated with 10 or 20 weight% nickel. The film thickness is nominally 10 to 20 microns thick. So the idea is we apply a voltage across that wire to heat it up. We also did some characterization. So we apply the voltage to heat up that fecraloy underneath the catalytic layer and then carry out the endothermic chemistry. Now, the whole single wire is put into a reactor that is in a small scale, bench scale setup where we feed in methane and steam, balanced nitrogen, atmospheric pressure, and measure for different conditions the product gases. So fairly straightforward bench scale reactor system. And here's a picture of the reactor. So the coil is spanning the cross section of the reactor. And being a reaction engineer, that you look at that, clearly that's a poorly designed reactor, but in the sense that there's plenty of room for bypassing. I'll get back to that in a minute. But here our idea was simply to get basic data for one wire, with next step down the line, putting in multiple wires that are individually controlled along the length of the reactor, oriented in different ways to minimize the bypassing. So let me show you some results. So what I'm plotting here is methane fractional conversion versus applied power. There's the flow rate and the W over F. The green line is, under these conditions, the equilibrium conversion for methane steam reforming and water gas shift coupled together. The red points are the uncoated wire, the blue points are the coated wire. Now, what you see is kind of an unusual result. Below a critical power, nominally 65, 67 watts, there's very little reaction. Once we hit the high 60s in wattage, there's a very sharp nonlinear jump to a much higher conversion on the order of 85%. Now, under these conditions, equilibrium states that we should be at 100%, nearly 100% conversion. So we're not there. We believe that that gap is the bypassing that I mentioned. Now, another point to note is the uncoated wire gives very little conversion over the entire range of power. So clearly the nickel zirconia is doing some catalysis here, which is not surprising. Now, again, that gap, we believe, is due to bypassing at this flow rate around the, in those regions where the wire is not. And we've been able to show that in more recent data. Now, in terms of temperature, which is the other axis shown here, we have to estimate the temperature by using knowledge of the measured voltage and resistance. We can use a simple energy balance with the correct correlation for the heat transfer coefficient. We factor in radiation heat losses. If we solve this nonlinear algebraic equation, we can get temperature at each power setting. And so what you can see is that upon ignition, for lack of a better term, we're at about 800 degrees centigrade wire temperature. Now, let's show a little bit more data. Zirconia without nickel is very inactive, so that's the purple squares here. Higher flow rate leads to more bypassing, very little effect on the point of transition to the high conversion state. Now, all these observations were working with Ram Ratnakar to understand this from a quantitative standpoint. He'll get into that more in the second talk today. Now, the distribution of CO and CO2 is shown here. On the left is the yield of CO, on the right CO2. And this is really showing a nice tracking with the equilibrium prediction, which is basically the temperature dependence of the reverse water gas shift reaction, producing more CO at higher temperature. So at least in terms of the thermodynamics, the activity of the catalyst, everything looks fine, but our head continued to be scratched over what is causing this jump in conversion. And the reason I say that is, being a reaction engineer, I've done a lot of work over the years on multiple steady states, and the first time we observed this, it certainly looked like a ignition that is commonly seen in catalytic reactions. Unfortunately, it's well known that that only happens when the reaction's exothermic. Steam methane reforming being endothermic is not a candidate for the so-called thermokinetic multiplicity. So we have to rule that out. Another possibility is we have a solenoid. Is it possible that a magnetic field is affecting in some way the chemistry in a nonlinear way? So here I'm showing the field lines produced by a standard solenoid, and you can see those lines going through the center there, this coil being catalytic in contact with a reacting gas. Is it possible that we're getting an influence of the magnetic field on, say, the adsorption rate? There is some evidence in the literature that magnetic field can increase the rate of reaction. We've not ruled out this as a possibility, so we're holding still on that possibility. Now, the third reason, which we seem to favor at this point in time, is what we call thermal electron rate enhancement. Let me walk you through that. But before I do that, I want to show you another experiment that we did. Now, the blue points are data that I've already shown you with the nonlinear jump in the conversion. The red points are data now where we take the same wire, cut it up, put it into a tube, and heat it in a furnace the conventional way that we all know in bench scale reactors. Now, the result with that is makes a lot more sense. It's a sigmoidal curve as a function of power and temperature, approaching very high conversion at high temperature, with this being an endothermic reaction. So what's going on? Why is the electrically heated catalyst so different than the thermally conventionally heated catalyst under otherwise identical conditions? Well, I kind of implied that, well, let me walk through this potential mechanism. So what I'm looking at is a schematic of the basic catalyst. So we have the underlying coil that is being electrically heated through the passage of electrons by application of a voltage. That is heating up the nickel zirconia film, and SMR chemistry occurs. Now, what about the possibility that a fraction of the electrons make their way into the zirconia layer? It's only 20 microns thick. There are small crystallites of nickel and nickel oxide metal on the zirconia. If you go back in the literature, in fact, it's pretty well established that zirconia has a conductivity that is exponentially temperature dependent. So the argument here, at least hypothesis, is that some electrons are making their way with the applied voltage through the zirconia layer that conducts. Maybe those electrons make their way to the nickel, and they do a electroreduction of nickel oxide, nickel hydroxide into nickel metal. Now, why would that be important? Well, it's known in the SMR literature that nickel metal is more active than nickel oxide, and certainly nickel hydroxide. So the big question is it possible that we're doing some electrocatalysis here that is causing the nonlinearity. The argument being that as we increase the temperature by increasing the voltage, we eclipse a threshold of temperature to allow some electrons to conduct through the zirconia layer. It's only a hypothesis right now, but that we're proceeding to look at that more closely. So let me close by saying single wire catalytic reactor does SMR chemistry quite well. Whether it's a practical reactor, we don't know yet. That's part of the next steps that we have in mind, which include directly measuring the wire temperature by IR thermography. We're getting that started. Probing other materials, that's a natural avenue to go, especially if we're thinking that the top layer is conductive. From a reactor design standpoint, the question often comes up about electrified reactors. What's the energy utilization? The standard question about reactors in general is what's the space-time yield? That is a focus going forward. Certainly catalyst life, if not sufficient, is a showstopper. But then reactor scale-up poses some interesting multi-wire questions. So with that, let me again acknowledge NYU for seed funding for the plasma work, Shell for this study that we're doing in collaboration with Ratnakar, and then finally the work of very talented students, in particular Elmer Ledesma and Meghana. Elmer is this guy sitting right next to me with the funny hat on, very talented student. So with that, I will pass the baton to Miguel.
Thank you, Mike. That was a great talk. So we're going to move on to the second talk, and we'll have some time for an open discussion at the very end. In the meantime, if you have questions, feel free to post them in the chat, and we'll have an open discussion at the end. So I'll invite Ram to the stage. So Ram Ratnakar, who you already saw some of the work that was done in collaboration with Mike, is a senior researcher at Shell. Have been at Shell for 15 plus years. He got his bachelor's from Indian Institute of Technology at Delhi, and then got a PhD at University of Houston. Ram have also been very active in the reaction engineering community. He's currently an editor-in-chief of the Upstream Oil and Gas Technology Journal, and is an associate editor for Frontiers in Fuels. So I believe Ram was having a hard time connecting via Zoom, but I will share his slides. And I think he'll be talking over his phone. Ram, are you there?
Yes, Miguel, I was able to join through Google, so
okay,
I think I can share the slides as well.
So go ahead and share.
Okay. Let's see. Can you see the screen?
Yes, Ram, we can see your screen.
Okay, perfect. And the slides are visible?
Yes, they are visible now. Actually, we're seeing the presentation mode, not the full screen mode.
How about now?
Now it's perfect.
Okay, perfect. Thank you. Oops. Thank you, Miguel, for the introduction. And Dr. Harold already went through detail on the electrified reactors. But in this talk, I will give a little bit more overview on the decarbonization efforts that Shell has been working on. And this talk is more triggered towards decarbonizing the hydrogen supply chain through electrification, specifically focusing on how we can carry the endothermic reaction using the renewable power. This specific talk will include some examples of steam methane reforming and ammonia cracking. The steam methane reforming work has been done, as Dr. Harold mentioned, in the collaboration with University of Houston, with my PhD supervisor, Dr. Bala Koteya, and of course, Dr. Mike Harold, Dr. Praveen Bolini, and the 3 students were involved. Meghna, who actually work on the catalyst synthesis and characterization. Elmer, that you already showed, Dr. Harold showed the photo. He works on the flow experiments, and Collins, who does more on the modeling specific to biomethane reforming. All these works are basically towards understanding the processes of electrified steam methane reforming and see the technical feasibility of it and what are the challenges, etc. So some of them I'll actually show it over here. But before I say anything, this is the cautionary note that we usually always present. You don't have to, I mean, you are more than welcome to read it. But just the crux is that do not buy any share of Shell based on my talk. So that is the summary of it. So again, just a little bit background why we need decarbonization, and all these things are pretty much known. I'm sure most of you already know, maybe even better than I do. But after that, I'll focus more on the electrified reactors, showing its novelty and how it can be coupled with renewable power and why, and a little bit technical feasibility that Dr. Harold already showed through experimental results, and then focus again on steam methane reforming and ammonia decomposition. So as we know, the CO2 has been increasing, and it has adverse climate change, adverse impact on climates. It is changing, and it could actually lead to several ecological, physical, health related issues. So there are so many efforts ongoing basically at the geopolitical level. Paris Agreement was one of them. So people trying to actually find out either to develop the CO2 free technologies or to eliminate the emission or at least reduce the emission. And for that, this is the chart that I am showing basically to show that primary emission sources are transportation, power, and burning fossil fuels for heat supply. So all these things, like just to give an example, like let's say we have a ethane cracker. This is ethylene manufacturing plant. 1.2 megaton CO2 is released per megaton ethylene produced from the traditional technology. And this number 1.2, that could actually go really high. For example, in steam methane reforming, it could go to 10 megaton CO2 per megaton of hydrogen produced, and so on. For the steel and aluminum industries, the numbers are significantly high. Like for example, aluminum, that actually ratio goes to 50. So there are so many issues, even though the production output of different chemicals and steel, aluminum, whatever you call it, may be different, but at the end, if we normalize it, there is significant amount of CO2 produced in these industries. And that's why several efforts have been actually made to reduce the CO2 footprint from these industries. And this work is basically some effort towards it. Now, of course, there are many decarbonization strategies that industries and even the academic researchers actually focus on. And here I characterize them into 3. Of course, it does not include all the other pathways, but one of the common pathway is that why don't we use a different fuel rather than fossil fuel, because it's the burning the fossil fuel that releases the CO2. So a lot of focus has been actually going on hydrogen, as you all may aware, that when you burn hydrogen, actually it gives the steam and it's carbon free. But the problem is that even though there are so many work has been going on hydrogen, we still do not have commercial scale hydrogen supply chain. What I mean by that is that, yes, we do have hydrogen production, commercial hydrogen production that is typically done using steam methane reforming. Now electrolyzers are also picking up, even their production capacity is not comparable, but the production part is there. Same, the transportation are also feasible in different route, but it is not commercially feasible to big scale. And the storage part is the one that has a lot of challenges. And we have wrote in 2021 a review paper on basically the whole hydrogen supply chain, giving the overview of every element of it, and focusing more on what are the challenges towards the cryogenic storage. Now, why I'm focusing on cryogenic storage? Because of course you can store hydrogen in gaseous compressed cylinders, but if you are using that, let's say in a gas station for that use, there is restrictions from the ISO that you have to have less than 5 ppm of moisture content in hydrogen to be able to use in hydrogen fuel cell vehicle. So those restrictions actually create a trouble when you are compressing, and especially through the electrochemical compressors, where the membranes are actually saturated with water, and because of the whole process, some moisture actually get entrained into the compressed side. Of course, you can use the mechanical compressors as well, but they all have some disadvantages. The current at the current point, the largest tank that we used to have is with NASA, which is 3,700 meter cube. And now Kawasaki, I think, had developed the tank of 10,000 meter cube, but it is still at lower end, as the comparable LNG tankers are like 100 to 200,000 meter cube. So we are still very far from there. The other way is that, okay, we can use the fossil fuels, and whatever the CO2 is produced, we can eliminate it either directly from the flue gases or from the air. And again, like, we wrote some paper showing basically what are the various sorbents that people can use, and a little bit of experimental and theoretical validation of this process. But again, it has the same thing. We still do not have the commercial scale processes for it. The third category that we can actually think of is that it is the fossil fuel that we use. Fossil fuels that are used in manufacturing industries are mainly to supply the heat. So like we have these gas burners. I'm not sure if you can see, but let me. So you have gas burners where the fossil fuels are, like, let's say natural gases are put, and then you have reactor, it burns. This is just an schematic, and then the heat is supplied through radiation as well as the hot gases that are in contact with the tube. And this actually releases, this is the reason why we get a lot of CO2 by burning these fossil fuels. So if we replace this by electric furnaces instead of these traditional furnaces, and we have this electric elements like here wire and plates, and then we actually use the Joule heating or any other electrical heating, like using induction or through electrodes and so on, and we use that heat to actually supply that for the reaction. Of course, if we are taking the electricity from, again, burning fossil fuel, it is actually bad, because then you are adding another process, and again you are using the fossil fuel, so it is not going to help. But if this electricity can come from renewable power, then it is a huge deal. You can reduce, eliminate. Sometimes you can also go negative. When I say negative, meaning that you, in some processes, CO2 can also be utilized, and that actually make seen as the negative emission. So we have wrote a little bit overview, as Dr. Herold mentioned, of examining multiple electrified reactor concept, and then see, and then out of that we actually found that parallel wire is very advantageous, and I'll explain that briefly in a coming slide. So the main idea is that this is your traditional furnace, and this is your, let's say, tubular reactor. You put the reactant and you get the product, and all the heat that is used is supplied by burning the fossil fuels, and as a result you get a lot of CO2 emission. Now when you have this electric component and all the heat is supplied by the electricity, then there is no burning fossil fuel. All the CO2 that is emitted over here is gone. Now, of course, this electricity, as I mentioned, could come with the CO2 footprint itself if it is coming from coal or different sources. But if it is coming from renewable power, then there is no CO2 emission, and all the amount that I was mentioning before, that 1.2 megaton per annum of CO2 that you produce if you are producing the ethylene of 1 megaton per annum, those CO2 are completely eliminated. And that is the idea that we wanted to pursue experimentally and theoretically. So with that, of course, you can have many electric components. So this is just a schematic where you have single wires that could also be arranged in a layer, and it can also be, the same layer can also be placed along the flow direction and so on. The other concept that we saw is the parallel plate, the wire mesh. This is plates with hole, like equivalent to the short monolith. This is the long monolith that this figure is, a similar figure is from the MUSE people. And then this is the typical tubular reactor where the electricity is passed along the flow direction. We saw all these things. Now, they all are basically based on the electrical resistance heating. And they all can be applied to many endothermic processes. Various researchers have worked on the monolith with foam, or simple washcoat layer, and so on. Now, these electric reactors usually give higher efficiency because most of the heat is basically utilized because they are in contact with the reactant. Now, that is the key point over here, that for example, in this case of wire, why it actually, it is much better than the traditional setting where heat is transferred from the furnace to the tube through the radiation. There are so many heat resistances that actually loses the efficiency. That's why we usually get 30 to 40% thermal efficiency. But in this case, the reactant is flowing through the wire. So there, and the wires are heated, and wire could also be catalytic, like if we are carrying the catalytic reactions. So they can be coated with the catalyst, as Dr. Harold showed schematically in his picture. So that way, your reactant, your heating and reacting elements both are the same, and the reactant is in contact with these heating elements. So there are very little heat resistances. So that's why you get thermal efficiency more than 90-95% in these reactors. Now, another key point I want to mention over here is that out of all these, actually parallel wire actually showed much better in terms of efficiency and design flexibility. And the reason being is that, like, you consider the tubular reactor or the monolith or plates, any of these reactors, what happens is that your flow direction and the direction of current are the same. Now, I mean, being a reaction engineer, you know that, like, this doesn't give much flexibility. If you want to, your space time is depending on this length, as well as the heating rate that you are supplying through electrical heating is also depending on the same length. So you actually constant, because you fix one length and then you're gonna fix the other quantities. However, in this case, your current direction is along the wire, while the flow direction is perpendicular to it. What it means is that you can select the reactor length, the flow length, independent of the current length or the voltage, the length across which the voltage is applied. Now, this actually gives the flexibility of designing the heating rate independent of your space time of the reactor. So this is additional flexibility that you get, and that is very helpful in designing. In fact, because of that, we actually shown that your reactor could be 30 times lower than the traditional reactors while keeping the production capacity same. Again, this is the schematic that Dr. Harold also showed. So the main idea when we do commercialize is that we have these electrical heated reactors, we feed it, we get the product, and then all the electricity that is given comes from the renewable power. And we did some calculation basically for the ethane cracking, 250 kiloton per annum capacity with 80% thermal efficiency. And what we found that we need actually 54 to 60 megawatt renewable power, and that could be actually provided by 18 to 20 windmills, assuming that every windmill is roughly 3 megawatt. So similar calculation can also be done with others, but this is just to show that it is possible on paper, and these are the power requirements. Now, of course, these ideas are ideas unless they are put in practice, and we start from the basic, which is seeing the experimental and theoretical feasibility. So, and this is not the first time that we have actually done the work. I mean, other people have already tried it. For example, even before Visman, there are some work that has been conducted on this topic. But this is something that actually very close to what we were looking for. And what they have is that you have this tube, the electric, and it is internally coated with the catalyst, and then they actually did this. They already showed the feasibility of this reactor basically, and what they found is very nice conversion as well. So and similar several of such work has been done in the past, and recently this work is quite picking up by many groups. So again, as I told that earlier, we did some calculation specifically for ethane cracking from and producing the ethylene. So this is the simple schematic of the calculation. Of course, we don't have to go into detail, but the point over here, the main point that I want to mention is few. First, in the traditional cracker, because of the lot of heat resistances, the temperature of the fluid and temperature of the solid, the reacting fluid and the temperature of the solid, the difference is roughly 200 to 300 degrees C. And that actually shows that how bad thermal efficiency that traditional crackers have. In our case, when we did this calculation, we actually found that the difference is roughly 70 degrees C, which is much lower. And the second point that I wanted to make is the size of the reactor. So just by we can actually have a miniature size of these electrified reactors. For example, the wires could be of the millimeter size, the catalyst could be in a micron, like 10 to 50 micron thickness, and so on. And all those things actually give rise to almost 30 times lower real estate footprint, comparing the same traditional technologies. So these two are significant improvement in our opinion. And of course, I'll show later maybe where the coupling with renewable power actually requires the possibility or ability to handle the intermittent nature of renewable power. And I will come to that later. So on this one, just to give a simple example of steam methane reforming, we actually did this thermodynamic analysis, and this is the isothermal line, this is the adiabatic line, and this is the electrified line. This is basically just based on the thermodynamics and simple pseudo-homogeneous model calculation, where we wanted to see that what would be the effect of space-time and the feed temperature on the conversion. And as you can see in these figures, that actually the electrified reactor can actually lead to very high conversion, much higher than the isothermal case. Of course, it will come at the expense of increased temperature. Here, you can also see another thing is that the space-time requirement could be comparable to actually your reaction time. And it is possible in our electrified reactors. And you can see that this space-time requirement for high conversion is roughly 0.1 second in steam methane reforming. Now, why this is important? Because let's say we are talking about renewable power. It has intermittency of 12 hours. Now, this 1 second, and then I'll also show maybe, I think, I don't have it here, but even the transient
do you mind?
Yes.
I apologize for interjecting. Do you mind closing in a minute or two so we have some time for discussion before we close the meeting?
Yeah, definitely. I'm almost done. So so this 0.1 second is much lower time, and this is also the time of transient. So if you have intermittency and if you are able to start or restart the reactor within 1 second as compared to your intermittency of 12 hours, that actually gives you the upper edge. You can turn it off and on anytime, while in traditional case, your transient time is quite a lot, as some of you may have that experience. And that's why this compatibility actually enables the coupling with renewable power. Because we don't have time, I won't go into much detail on the sensitivity. All these things are published. So in our previous papers, I'm going to actually skip that as well. The second example is on ammonia decomposition. Now, this is towards decarbonizing hydrogen supply chain. As I mentioned, there are like transportation issues as well as the storage issue. So one of the pathways that people actually think of is why don't we convert hydrogen to ammonia and then carry it, because ammonia supply chain is very well established, and then at the end user side we can actually decompose it. Now that decomposition could also release a lot of CO2 if it is done traditionally. So here we actually do that with electrified reactors. And this is just simple work basically done where I'm showing basically that there are so many discrepancies or inconsistencies in terms of kinetics of ammonia decomposition. It is not accepted, like there is not a single form is accepted. And I actually gave the single form. That paper is in the review. And this also actually gives the same signature as we see that for steam methane reforming. And we have done the similar calculation for dry methane, bi-methane reforming, as well as ethane cracking, and we find the similar characteristics, basically. So just to summarize, we all know that net zero emission technologies are required, and electrified reactors could be one of the possible pathway to decarbonize the chemical manufacturing as well as the hydrogen supply chain, depending on how do we use. And the electrified reactors that we present based on the wired reactor, they are capable to enable the coupling between the renewable power. I think
thank you,
with
Ram.
that, I will, yeah, thank you.
Thanks so much. Wonderful presentation. And I think the combination of the two presentations is, a clear example of how some of the DC-MUSE members collaborating with industry can really lead to a substantial push in the industry. And this is the type of things that we really want to convey in these type of seminars. So as you see these type of collaborations, and if you have needs for academic collaborators on either electrified reactors, electrochemistry, or plasma, please don't hesitate to reach out to either Simon Mashala or Frank Valese or myself, and we'll be happy to connect you with the rest of the DC-MUSE team. So with this, we don't really have that much time for discussion. I'll start with sort of a summary of some of the questions that I see on the chat, in particular for Mike. It seems like there were several questions about the choice of catalysts. Is there a possibility to use different metals? Is there challenges with stability on the addition of those catalysts with the electrical wires? And in particular, there were also comments about what are the resistivity and I guess like what are the trade-offs between resistivity and catalytic activity on these type of reactors?
Yeah, very good question. Yeah, we had to overcome some challenges on the adhesion front, but we think we've optimized the catalyst preparation. Those details are shown in the paper that I mentioned. We are looking at other materials. Certainly one of them is nickel alumina, which is the conventional catalyst for steam methane reforming. I do have data that I can't show you today, but it does paint a picture that the mechanism that we're proposing, the third one, is real. And the linchpin is the fact that alumina is an insulator, zirconia conducts, and you get qualitatively different behavior with the two different catalyst supports. As far as the resistance, for one of the data points that I showed, I think voltage of about 13 or 14 volts, the resistance of about 3 ohms to give the power of nominally 65 watts. So that's a tidbit of information. I don't know if that's sufficient, but that's ballpark numbers. So materials integrity is critical. There were some cases where with extended use, there would be some flaking off of the layer, off of the underlying metal. So more work needs to be done on material science.
Yeah, thanks, Mike. I see a question about long-term stability and coke resistance of this metal wire Joule heating. Perhaps either or both can comment on that.
We did not get any noticeable coke formation. Now that might be because the water to methane ratio is about 4, and water provides the decoking activity through the water gas chemistry. I think I saw another question about why is the conversion so low below the threshold, and the paper describes that in more detail, but in a nutshell, the surface temperature of the catalytic layer is a lot lower than the wire temperature due to the existence of gas side heat transfer limitations. The Reynolds number is not very high, and so there's actually natural convection factoring in to the experiment that we carried out. So basically, the conventionally heated catalyst is hotter at the same power as the electrically heated catalyst before light off.
Just
Thanks,
on the coke formation, we are also actually writing one paper where we actually have done the comprehensive thermodynamic analysis for bimethane reforming. That includes the dry methane reforming as well as the steam methane reforming, and it actually gives you basically the zone where carbon would form in terms of pressure, temperature, and composition. So feed composition, and where we have done these experiments and modeling actually is out of that zone.
Thank you, Ram. So I will encourage you, if you have questions, just put them on the chat. We'll share the chat with the speakers, and feel free to reach out to them directly with questions. We only have 1 more minute left. I'll ask one question myself. Sort of taking a step back and looking at the broader picture of electrified heater reactors, we've seen some examples of Joule heating in your presentations, but there are other groups that are pursuing other ways of heating via inductive coupling heating, microwave heating. Do you have any perspective about some of the advantages and disadvantages of different methods, and where you might want to use one versus the other?
Ram, do you want to take that one?
Yeah, sure. So actually, that is a great question. I mean, we are actually working on analyzing these things. We in the as I said, in upcoming paper that we are writing on the bimethane reforming, we actually have put a comparison table of these technologies. It all actually boils down to the efficiency and the time scale of heating. So in case of plasma, it actually gives the surge of the power, and you may not be able to actually capture all the power instantaneously. Of course, otherwise you're gonna go to the equipment failure limit. And then as it dissipates, you are utilizing it, but then you already lost the efficiency. That doesn't mean that it is bad for some application. In fact, some application it could be very good, where your time scale of the reaction is very fast, and you have to arrest it immediately. So it really depends on where, which application, the efficiency, the time scale, all those things. There are so many factors that you have to compare. Whichever gives the additional flexibility, in my opinion, would be the best design. But you may not always be lucky, and there is not one thing that is better for all the applications. So, you know, but we are working on those things. Yeah.
Thank you. Any last comment, Mike, before we close it?
No, just a lot of challenges in the catalysis reaction engineering space for this area, and I hope that others join in, and we're really happy to see industry participation in this webinar, which tells us academics that maybe this is somewhat relevant, at least right now anyways.
Yeah, for sure. We'll take that message. And thank you so much all for joining. We'll be having more of these webinars in the coming months. So be on the lookout for an email from Frank and Simon, and looking forward to continue the discussion. So thanks, Mike. Thanks, Ram. Really appreciated your talks, and I'll see you around.
Thank you, Miguel.
Bye.
Thank you.
Bye.
Thank you for the opportunity.